First thing I want to do is ask you whether you made any progress with the C. Are you having any difficulties? Huh?
We're doing it actually. We do it in the
So one thing I keep telling students is, if you know how to do it, it doesn't mean the computer knows how to do it. So you have to remember, it's not a very intelligent system, the computer. You have to painfully tell it each and every detail. So even if you miss something like converting from radians to degrees or the other way around, it's going to give you the wrong result. And that's not because the method is wrong, it's because the implementation details are wrong. So debugging often calls for a lot of patience, and you get better at it when you get more practice. Okay, now we're going to finish up this topic on the control strategies, typical open loop versus open loop really means no control strategy because you're not monitoring the variable of interest. Closed loop is where you achieve that. And so I posted in a separate folder, this folder, open loop versus closed loop, 4 documents. And I'm going to start with this. I did a little bit of this yesterday, but before the end of today, I'm going to sort of give you an exercise. It's voluntary, you can do it just like this is voluntary, but you learn a lot because you'll be actually guiding the robot to go to several waypoints. And that's one of the major things that robots are expected to do. Next week, I'll try to give you an exercise where the robot avoids obstacles or maybe uses a wall, which is an obstacle, to guide itself. It's the same thing because you can't follow a wall without trying to avoid it, right? So it's a kind of a wall following algorithm, and that will fit in with the cognition topic, the high level intelligence, which is the last topic we'll do. So all these other programs, 2 of them are MLX files, live editor files from MATLAB. If you're not familiar with it, you'll get a chance to become familiar with it. These 2 are going to act as support for that exercise, where you implement closed loop control. And then this is the program where I'm doing open loop control, but you can take that program and modify it and make it closed loop control in doing the exercise I'm going to give you. So this will be a springboard to completing the exercise with the help of these 2. So we'll start with this document. It's a PDF document, has some fancy figures, and let me show it to you. Okay, so this is what I drew, except that it's has more details now. So some change in terminology. I use C and R and so on, and I was trying to recollect it from the last time I taught controls, which was over a decade ago. The C and R, remember? R was the input and C was the output. But that terminology has been dropped. It used to be there in all the control specs. Now they call it, maybe input is called a set point. So a set point, maybe SP, we use SP. So a set point is what you want the control system's output to be. So you're setting the point, you're saying, okay, imitate this, or copy this at the output. So the set point is the input, and he calls the output, but I would rather call it desired output, So maybe DO for desired output, and set point SP. Okay, now, so you're forming the error because if you, as I said, in closed loop control, you have to monitor the quantity you want to control. It's not enough to monitor time and say, I assume the velocity is, constant, and velocity times time is going to give you distance, so I will achieve distance indirectly. It doesn't quite work like that because the velocity will never be constant. There'll be ups and downs as you hit a bump in the road. So therefore you have to monitor distance. You can't monitor velocity, time. So the set point plus and the output, desired output, TO, you subtract that and you get E of t, the error, right? And then you have the controller. So here you see details of the controller. Yesterday we only discussed proportional control. But in proportional control, you don't have these 2. So these are removed. So Ki is 0, Kd is 0, and Kp, the proportional, we call it proportional control because the output is some constant times the error. That's why we call it proportional control. Here, the output here is Ki integral of the error. So the integral meaning the area under the error curve. What is the error? It's the difference between set point and desired output. And finally, the derivative part of the control is Kd times the derivative of the error. All of these are added together and fed to the process. The process is your robot, in your case. So the robot is given an input so that the desired output tries to track the set point. And the set point can change with time, as it will when you're trying to hit an enemy missile. So the enemy missile is changing its position with respect to time. So this can be a function of time, and therefore you want the output also to be the same function of time, because you want to hit the enemy missile. Okay, now, any questions on this? Alright, now, what is the effect of these three? Now, this one makes the most intuitive sense, because if the error is large, you want to act quickly. You want to have a bigger reaction, right? So, for instance, if your car is going off the road, then you try to bring it back to the straight position, much more violently. So that's what this does, Kp times E of t. Kp is something that you choose, and it's going to apply a strong control action if E is larger, not so strong if E is smaller, because Kp is the multiplying constant. That's why you call it proportional constant. We'll talk about this a little bit later. They are less intuitive, but let's go and look at what these do qualitatively. It'll make more sense once I show you some waveforms from the Wikipedia article. So increasing Kp, if you increase Kp, you're going to find, actually there's no point in talking about this, we'll get back to this because we need figures. So let me show you figures. So this is the Wikipedia. So what is going on here? So this is your input. Reference is also the set point, same thing. So you're telling the robot, go at 1 meter per second. The robot is at rest, and you say go at 1 meter per second, right? That's called a step input. So the step input is basically a step. The robot is at rest, and you ask it to go at, here it is 1 meter per second. Now that's your set point. The output is not going to immediately get there, because remember dynamics and all that, right? So the system has a sluggishness to it that is part of the system. You can't do anything about it. You have to accept the system as it is. You can't change the system. That's control engineer doesn't have the ability to change the system. So you get the typical response that looks like this: the purple. So it's characterized by the larger Kp is, the more the overshoot. So you see how you have trade-offs in life? Because if you put a heavy response, how will you do that? By increasing the value of Kp, then you'll get an overshoot. You get a large overshoot, undershoot, and so the system is going to take a while to settle down. Okay? So it's going to get there very quickly, but it's going to overshoot. So once we know this, then we are in a position to understand what Kd does. So what if we don't like this huge overshoot? Okay, let's go back and look at the original document, which is this. Look at this down here. So if you plot out E of t, and it's possible for you to plot E of t, because obviously you have the set point and the response, so you can find the error. So how will that look like? Let's take a look. So here is the set point, and here is the response, right? The error is set point minus response. So the error here will be negative initially, set point minus response, and then the error will also oscillate, because at this point the error is 0, right? At this point the error is 0, 0, 0. So the error is going to oscillate around 0. Do you get that? is going to go like this. So what does it mean if I multiply Kd by dE by dt? If you plot out E of t, you will find out that Kd dE by dt is acting as a brake on Kp d of t. So it is going to reduce the overshoot because based on, so this is a predictive term. Anytime you have a derivative, remember a velocity model for a robot? The velocity model is predictive. It's, if you have a certain velocity here, you can predict what's going to happen in the future, right? So this term, Kd dE by dt, will actually subtract from the first term because of the sign of E of t. See, d by dt of E of t. So you can have both positive derivatives and negative derivatives. So what it will do is, it will slow down the overshoot. So it damps the overshoot because that large overshoot is not good, in a practical system. We'll be doing like this. So Kd acts like a damper to reduce the overshoot. But of course, the response is going to be slower than with proportional control alone. As I said, trade-offs. Everywhere in life, in engineering life, you have trade-offs. So the Kd term actually decreases the overshoot, but it's going to slow the response down. And that's what these words say basically. Now, how about this last term? So typically what happens is that when you have a control system, you end up with a steady state error. It's not shown here, but if you actually draw this, it will not level up with the set point. What will happen is, it will flatten, but there will be a constant difference between what you want and where you eventually saturate. So that's known as the steady state error, meaning that eventually you get a difference between the set point and the actual response. And proportional control cannot eliminate that. It just can't. So do you have to put up with it? Well, you don't, because if you look at the third term, which is this one here, notice if there is a non-zero error, then this term is going to build up, correct? And so Ki times the integral of dt dt actually adds a term to the control response that will address that. So this is basically for the purpose of eliminating steady state error. So this term eliminates steady state error. You don't have to have this or this, you can just go with this. And in fact, in your exercise, it works just with Kp E of t. Because we don't want to make this too sophisticated, we just have a week to look at it. So therefore, you don't need this. But I'm saying in general, this is known as PID control, proportional integral derivative control. And actually, this addresses the steady state error, this reduces the overshoot. And basically, that's what I'm saying here. So this is going to be useful in your exercise, because when you try to get to a waypoint, right? I told you there are two things you're going to do. You're going to check for whether you're in the zone of the waypoint, right?
Yeah.
You're going to say, am I in a little circle drawn around the waypoint? It has to be a little circle. It can't be a dot, because it's not possible to reach the waypoint exactly. It's just not possible. But if you're not pointed at the waypoint, then it doesn't matter. That check will never succeed, because if you're driving this way and the waypoint is here, then obviously, that check is never going to be satisfied, right? And the distance will actually increase from the waypoint. So therefore, you also have to steer. So the inner loop, you have to steer constantly towards the waypoint. And that is where you're going to use proportional control. You're going to use Kp on a heading error. So E of t is going to be a heading error, the difference between the set or the desired heading and the actual heading. And therefore, you're only going to do proportional control, and this value of Kp is very important. Make it too large and you'll find the robot becoming unstable, which is the huge overshoots. It'll make the robot, turtle 3 will become unstable. So don't give up on the program just because it doesn't work. Make sure everything else is working, and then you can dial down the value of Kp, and sure enough, the heading will be under control. And once you've done that, you can play with all these parameters. Suppose the tolerance of reaching the waypoint is bigger, make it bigger and see what happens. Suppose, if you want to make Kp bigger, the heading error correction, make it and see what happens. It'll be going like this, right? So you can see all that once you get the program working. done that. So let's go look at the Teams folder to cue us on what is the next item on the agenda. So we're going to do these two, but first we're going to do this one. So this M file is already there. Pull it down from Teams into your MATLAB directory, and you can run it along with me. So I'm going to have to fire up, the usual VMware followed by Ubuntu and then the ROS, the people. Okay, so I go through the usual routine. Okay. So everybody fire up this program. I'll fire up Ubuntu and Gazebo first. So yesterday I was talking about the jitter, that is a glitch in the Turtlebot 3. So for some, I don't know, it's not when you launch the empty world, but in some other programs, the Turtlebot is just sitting there and you go to the bathroom or for a cup of coffee, you come back, you notice that it's actually spinning slowly, So that's why within a MATLAB program, you need to cancel the jitter by resetting the state of the robot. And you're going to see that part of the code, I think, in this program. And this is going to be useful to you in your exercise because, what I'm doing is I'm giving you little pieces of program that need to be in your final program to do waypoint control. So let me fire up MATLAB. It's already fired up. So you know to find your IP address, ifconfig in a terminal window. So as I was saying yesterday, there are some standard parts like this cleanup, and then the ROS shutdown at the beginning and also at the end. So remember, if it's an eternal program, then it will never get to this ROS shutdown because you'll interrupt it with the Control C, ROS core will still be running. In ROS 2 we may not have this problem because there apparently is no ROS core. But right now we do have the problem, so we put a ROS shutdown here and we also put a ROS shutdown there. So clean up, shut down the ROS, and then you set up your IP. Okay, then you need to create your publishers and subscribers. So you can basically copy this into whatever program you're writing. Unless you have a new publisher, then you have to add that publisher. So I'm creating a publisher. Okay, this is the new stuff. Okay, I told you the robot is kind of moving sometimes. It's a glitch which they have fixed in the next version of ROS. But if you don't fix it, you go for a coffee, come back in 15 minutes, the robot will be pointing here. And that may upset your program. Maybe you're assuming that it's got to point in this direction at start. So therefore, there is a new publisher here, and that is Gazebo set model state. That allows you to pick up the robot and put it anywhere and orient it in any which way you want. That's all it is. It doesn't have to be back at 0, 0. You can put it at 6, 8. You can give it a 45-degree orientation heading, anything you want. You can minus 135 heading if you want, degrees. But here, we want it to reset in the origin position. So, this is what it returns, right? And then using that, I create a message structure. This is my own name, that's my own name. Set model state message. That's what I've called it. And then I give it a little bit of time to actually do it. And then here I say, I can now reset the Turtlebot 3 to desired position here or to cancel jitter. So it can be used for two purposes. Maybe your program is run like this, right? And you want it started again because it didn't work, right? You can always go and hit reset world, right? But you don't have to because this will take care of it. You're bringing it back to the origin, okay? And that's a useful thing to have. You can also reset it to any other position I told you. You would have to change X and Y for that particular need. How about angles? Now, angles are a little bit mysterious because in robotics, they are handled by something known as quaternions. You can't use regular angles because they have problems, There's two issues associated with them. We'll discuss them this afternoon. But just take it from me. that the angle does not have to be reset here because the default angle is 0. So you don't have to put it explicitly. It's automatically assumes 0 if you don't give anything else. So x and y, I make it come back to 0, 0. Okay? And then you can try it by putting like 4, 2 and see what happens. The turtle ball will be thrown to 4, 2 with an angle of 0. 0 is the default. Okay, now, so I reminded myself that for orientation I have to go a little bit further because I have to set up the quaternions. This x, y, and z is not the same as this x and y. I don't know why they choose that because it's very confusing, but it's x, y, z is for the quaternion as well as w. So I just put it here and said that's the default, but if you really want to make sure, then you should also do this part. You should uncomment these. It's not needed because the default works. Is it okay? If you're not confident of the default, you can set the quaternion to be 0, which gives you a 0 angle. We'll get to that exactly, the mystery of the quaternions. Okay, and then you publish. And then you can actually drag the robot away with your mouse and it will snap it back to the origin. You can see it actually works. So it is set model state. Now, I'll get back to this later. I'm saying that angle wrap is not an issue for this implementation since we turn through relative angle. I'll get back to that after I, remind me if I don't, to explain this. So angle wrap basically we discussed yesterday. The angle cannot be larger than 180 or smaller than minus 180. Because in robotics, right, you have the base range is 180 to minus 180. Not 0 to 360, it's plus 180 to minus 180. And if any angle is outside that, it might still be correct, right? Because what is 180 plus 60? 240. But 240 has a corresponding number in the allowed robotics range. It wants that because you can't give it 240 because what will often happen is maybe you need to go here, but because you're giving it 240, the robot will spin all the way around. So you don't want that because it's an odd way to go to a point here, by spinning all the way around. That's why you have to work in quaternions. You cannot work in angles. You have to unwrap them, bring them back into the 180 to minus 180 range. There's also another issue known as gimbal lock. That's hard to explain. We'll do it this afternoon. With regular angles, you get something known as gimbal lock, G-Y-M-B-A-L. So Apollo 13 had a gimbal lock issue back in the 70s when they didn't know much about it. And they suddenly had this problem, and it could have been quite severe, but they managed to solve it on the fly. So we'll talk about it this afternoon. Okay, then you create the regular set of publishers and subscribers. Create a publisher for velocity and 2 subscribers for odometry and model state. I told you yesterday about model state. If you want to use it, use it. If not, don't use it. It's not available in the real world, only in a simulator. So here's the command velocity to which you publish, and here's the odometry to which you subscribe. And then you create, so basically, you call this subscriber, and then you get an instance of that. Model state, subscriber, model state, subscriber, or not. I'm going to show you in a second how I knew, how to set it. Once I run it, I'll be able to show you. So I populate the VEL message, right? I need to populate it. For that, I have to first create it. I'm just creating it here. And then I populate it. 0.20. Now, what am I trying to do here? So I shouldn't be explaining the program without telling you what I'm trying to do here. So the robot is pointed down the x-axis, right? I'm going to make it go along the sides of a triangle. An equilateral triangle, each side is 3 meters. So each angle is 60 degrees, right? So it's going to go like this and back. Except that you're going to find out that it doesn't close the triangle. The triangle will not close because you're using open loop control. So equilateral triangle, go over this way, turn, and come back to the origin, right? So that's what we're going to ask it to do. That's the problem. Okay, so I set up my forward velocity. So remember, I'm going to execute this in a very crude way. I'm just going to go straight, assuming that I won't be pushed off the track. So by going straight, I assume that everything's perfect. I'm going to end up in the next vertex, right? But of course I'm not. You're going to see when you run it. Then when I reach 3 meters, I'm going to stop, and then I'm going to turn through, stop and turn through 120 degrees. The angles are 60, but you'll have to turn 120. You get that?
Yeah.
The angles are 60, but in order to look at the next vertex, you have to turn through 120 degrees. So I'm going to stop and turn through 120 degrees. When I've achieved 120 degrees of turn, I'm going to stop, and then I'm going to go forward to the next vertex. And then I'm going to do the same thing again. Turn through 120 degrees and come back. It's open loop, because I'm only measuring the time taken to go 3 meters, and I'm measuring the time taken to go through 120 degrees. So that's very much open loop. I'm not monitoring the angle achieved. I'm just saying turn, I know the rotational rate, so hopefully I'll end up with the right orientation. Right? Okay. So I just made some choices for the forward velocity for the straight segment, 0, 0.2 here. And for the turn, stop and turn, the velocity of turn, right? Because the forward velocity should be 0, only turn velocity. I just made it pi over 10. That should be in radians anyway, so pi over 10 is in radians. I could have made it pi over 20. The beauty of a program is you can experiment with those values and see whether you get better results. Change it a little bit, make it very high. It's never a good idea to make it too high because you lose control. I gave you the example of trying to turn into your driveway and you're coming at a very high speed. You're going to miss it. So that applies to a robot in gazebo also. So maybe this is too high, I don't know. This works. You can try it with other velocities. Okay, then I initialize the data. The 3 sides. Now the reason I do it is I can change it to any triangle, not necessarily equilateral. That is the beauty of not using specific numbers like 3. When you start using specific numbers in a program, they call it introducing magic numbers. Magic numbers in the sense that if you look at the same code a month from now, you wonder where did it come from. So it's never a good idea to introduce a 3 further down. It's better to define it as a variable and write a comment, lengths of triangle sides in meters. So you can change that. This is the angle of turn, except it isn't. 60, 60, 60 is not the angle of turn, it's 120. So the real angle of turn is 180 minus A and GT. Convert to turn angle. So these are the angles of the triangle. And this is these are the angles, in terms of your turn, the needed turn. Now angles, you're better off working in degrees because human beings relate to degrees and not to radians. But somewhere later you might have to convert it to radians. Keep that in mind. Because if I put radians here, then you're going to say, okay, what is that again? And how do you convert that to degrees? So let's keep it in degrees for now. So I receive the latest rotometry data and I receive the latest model state data. And then I do the same thing that you saw in the other program. Yesterday's drive in circle. I use a deal to deconstruct the x and y coordinates and put it in ODAM pose 1 and ODAM pose 2. And then I do the same thing. I then park it in x and y. There might be 1 or 2 variables too many in this approach, but I like to do things in an organized manner. And now I'm ready with my first set of velocities. I pack it into the structure, straight and rotation. And you know this from yesterday's discussion. We don't want to run any loop in a real-time program faster than it needs to run, particularly when you're dealing with mechanical systems. So you define this rate object, okay? You define this rate object, and then you're going to use that to time the loop. So this is the main part of the program. All of that was set up. So you have a for loop for the 3 sides of the triangle, right? So you don't have to do triangles. You can do 5-sided figures. Then you change it to 1 to 5, right? It can be anything you want. You may have 7 waypoints. Waypoints are intermediate points on a robot's path. So you can hit 7 points and come back. That's what you're going to do. So in which case you change it to 7. Go here, go here, go here, go here, go here. 7 points, like a security patrol. Is that okay? So that's what the outer for loop is about. The number of points or the number of times you want to do it. So, what is the time taken or your estimated time to go 3 meters? So LSNS, right? Because remember, here it happens to be the same. There you go past it. Yeah, here it's all the same, but it doesn't have to be in general. So I'm calculating I'm calculating the time it will take to travel the first side of the triangle. And then again I fill the well message structure with the velocities corresponding to going straight. This happens to be 0. Don't put 0 there. If you put 0 there, it becomes a magic number. That's why you use variables, because then you won't understand 1 month later where that 0 is coming from. Start driving straight. So that happens only when you send this message, right? So you need to send this message to this topic. And then you're ready for the inner loop, right? What is the inner loop? You're constantly checking whether the time is up. I'm supposed to be driving for, let's say, 10 seconds. Are the 10 seconds up? Are the 10 seconds up? It's open loop, right? Because driving 10 seconds, assuming a constant velocity, is just a guess. Your velocity can never be constant because initially you're at 0. So you have to accelerate to the velocity anyway. So that's not a good way of driving. Right? It's like saying, I'll drive a certain amount of time to get to Chennai, no matter the traffic. And that doesn't happen, right? Because you've got to monitor your progress. And drive as long as it takes to get there. Driving for a certain time is not going to do it. Okay, so this is my time counter, and then I reset the stopwatch and say start now, and you'll see that this part is similar to your drive in circle program. While RTT is less than TS, do this while loop. And here I update RTT by using that rate object, this part of it. It's a method within the rate object. And then I keep driving. Remember I told you that robots need to be told constantly to drive. You can't just stop, because then most robots, Turtlebot 3 doesn't have that programmed in. Most robots have something known as a watchdog timer. So watchdog is, if you don't receive any commands, it's going to say, no, I'm going to stop for safety purposes. So this one doesn't seem to have it. So send the message and then update your odometry. See, very familiar code because it's the same code we've used before. And then I burn the rest of the loop time. So this is the loop that drives straight. Here you have another loop for driving, for turning while you're stopped. Because remember, this way, turn. This way, turn, come back this way. So, got it? So we're going to have 2 while loops. Now we're going to turn and point to the next vertex. So that loop starts here. But we have to do some setup for the second while loop. I change my velocities, right? First I stop the robot, by the way. Once I get out of this loop, I know I have covered the time. I don't know what distance it will be, but we have covered, we've driven enough. And so I stop the robot. And then I set up the turn in place. So that's not normally how you drive. Sometimes you have to stop and turn, right? You can't park on the fly. But most of the time you like to curve through intermediate goals. You don't necessarily have to stop and then go. But I'm trying to make it simpler here in this program. So how much time does it take to turn? So see here, ANGTNS, and that is, it will be 120, 120, 120. So ANGTNS. I'm trying to not use magic numbers. So right here, TR, time for the turn, is 120 degrees times pi by 180. You know, if you miss this, the program will not work because the rotation turn is in radians per second. You can't put degrees here. You can't just say A N G T N S and remove this. So this is what is involved in programming correctly. The computer does not know that you meant degrees. It wants you to convert it to radians. And this is what you're doing here, pi by 180. Then when you divide by the rotation turn velocity, which is, you know, in radians per second, everything is fine. You get seconds. And then I fill the well message container with the turn set. Here, VEL turn is 0, and ROT turn is whatever you set it there. I believe it was pi by 10. And then I say, okay, start turning. Then I initialize the counter. So if you forget this, then it will still carry the value of this loop. So these are, you know, this is how you get better and better as a programmer. Because if you don't reset it to 0, right, RTT, and then reset the clock or the stopwatch, then the program will not work. So here it is. And then I have my turn in place loop. We find the structure very similar because I'm just turning for a certain time now, right? I've already got the velocity set up in PubWell, right here. So identical kind of a loop. So basically copy the earlier one and if there's any changes you can make it. Is everyone clear about that? So notice again, I burned the rest of the time. Just like I burned the rest of the time. I don't want that loop to run at a faster speed than the computer can run it. I want it to run at 10 hertz, 10 times per second only. So you can play with it and see what happens if you make it 100 times a second. You won't find much of a difference. What if you make it 5 times a second? Yeah, if you make it too slow, there'll be a difference. So you can, once you have the program working, you can just use it to learn. Is that okay? So then you stop the robot. And of course, this is the end of the for loop, so you do it 3 times. This way, and then back here. Now, here's the plot. And then when it's all done, you know, stop the robot one final time and shut down ROS. So we're going to run it, and you're going to find something surprising. The second time you run it, you won't get the same path as the first time. I believe, as I said, that Gazebo adds a little bit of noise to simulate what a robot would do under realistic circumstances. Maybe the tire catches something that it did not the first time. But the main thing is that figure will never close. You won't get a triangle, it will be closed, but you know, it won't be an actual triangle, equilateral triangle. Okay, so you're going to run it, and in order to do that, I have to switch to Gazebo so that you can see what's going on. So now it's woken up. 3 meters is 3 squares. Stop. Yeah, it did. Approximately okay this time. Now we can't tell whether that's 120 degrees because, you know, it's a perspective issue. I don't know exactly what the angle is. I have to see from above. That seems about right. And it seems to be missing quite a bit, I would think. Yeah. It's missed, right? It's missed. And I'll show you the plot in a second. Come on. What happened to the plot? Oh, here it is. Do you agree? So that's just a glitch. It's a plotting glitch. It's got nothing to do with anything else. So you see, it clearly missed and ended up at 0.5 and a negative value of y, maybe 0.25 or something. Now we can run it again and see what happens. So what we do is we go back here, run it again. I wish I could show you the gazebo screen because it's going to move the robot back. You see, the robot is here. The robot is off a little bit. So when the reset command is executed, it will move it back. But you won't be able to see that because I'll have to juggle the screen in order to show you both. Maybe, okay. I just run it, I got fast. You can't see this here because by the time I go there, it will be too late. So, oh no, yeah, you saw it, right? Yeah. You can even throw the robot up in the air with that command. It bumps because they built physics into it. It might even fall over because it depends on the physics. See, it's off the line now. Can you see? It's off the line. Yeah, clearly off the line. So that's, I believe they are programming some noise in there. Huh? Somebody ask a question? It looks even more off. I don't know. Same kind of error, yeah. Except it stopped on the axis. You see, it stopped on the axis. Y seems to be okay, but X is again off. And here's what you get. You see this here? Did you see this? So it veered off on its own, like real vehicles will do. And this time it made it back to Y equals 0, but it was off on the X. So if you run it many times, you'll get different results. And it's actually a nice way to spend a Sunday. No, I'm joking. But it's quite fascinating, there's a randomness to it, just like the real world. You don't want to kill that randomness because that is the world. Any questions? So the entire program structure I unraveled for you. So this exercise I'm going to formulate, I'll do it over the lunch break. You can give it a shot, it's one basic thing that a robot is expected to do. So what you're going to do is you're not going to go with this open loop strategy. And the next two programs I'm going to discuss is going to help you address that homework because there are some little tricks that you have to be aware of. So the basic logic is one thing, but also things like quaternions, how to deal with them, how to unwrap an angle. That's what the other two programs are about. So you're all familiar with an MLX file, right? A live editor file. It's a very good way of writing a tutorial for yourself. But it slows down execution. So in your exercise, don't try to make it an MLX file because it'll slow it down. So the robot has a current heading, right? Now remember, in this program, we are not correcting for heading. We are just going straight for 3 meters, turn through 120 degrees, go straight for 3 meters, turn through 120 degrees. So when you replace that file, we'll let these fixes take place. Otherwise they are distracted. I'm going to show you my launch file and you can take a look. Except that you may have to do a Catkin maze. These are indented, right? This one doesn't matter because it's within these start and end tags. Everything else lines up this way. See here it doesn't matter because it's within the start and end tags. Same thing here. Insert these lines in the original package. I don't think it matters because we have this end tag and the start tag. Now one thing I didn't show you, but now is the best time to show it, is to look at the variables we generated. There was some question about, about all this. Where am I getting all this from? So go to set message, right? Set message. Here it is. Pose. Position. X. See? This is where I'm getting the structure of my variables. Right there. See? That's the variable for X. Similarly, for the quaternion part, you can do it by, again, going to pose, orientation this time. See here? So that we will study this afternoon. This XYZ is not the same as the other XYZ. XYZW constitute the quaternion representation. We'll get to that this afternoon. So once you run it once, all the variables are here and you can sort of probe them. Or you can look up the documentation on ROS.org. All this is there on ROS.org. Okay, now back to adjust heading. So the robot has a current heading. It needs to rotate to align in the direction of the goal. So you see the problem in the previous program? It's not pointing at the goal. It's just a rough guess, right? Go forward for 3 meters. Sometimes it's going this way, right? Sometimes it's on the line. But you have to guarantee that it's pointing to the next goal. Therefore, you have to adjust the heading. Let me remind you, the heading angle is the angle made with the global XI axis. That is the definition of heading. The global XI axis. So you need to constantly adjust that towards the next destination. Then you don't even have to stop. You can go right through the vertex and it will automatically turn to the next vertex. That's how you drive. Nobody drives forward and then turn, forward and then turn. You should be able to curve around that whole triangle. So, how do you adjust the heading? You need a control system for that, based on the principles I showed you earlier today. But you need to calculate the heading error. The heading error is the desired minus actual. Theta desired minus theta current. Current is actual, right now what you have. Is that okay? Similar to set point minus desired output. Same thing. The heading error is then used to set the robot's turn velocity omega to make the robot continuously point towards the goal. That is how exactly we drive. If you want to go down a lane, right? You constantly turn, right? To adjust yourself. That's the same thing. So the control system should try to dynamically minimize the error. You can go proportional integral derivative control, but let's just stick to proportional. So even if the goal is moving, let's say you're chasing your dog, right? The dog is moving. You constantly change your heading and head towards it. Now to catch the dog, you have to be faster than it's moving, right? That's obvious. To hit an incoming missile, you have to have the dynamics to hit the missile. All that is separate. But if you don't track the missile, then nothing else matters because you will not be able to hit it. So here's my example. Listen carefully because it has many things in it. So I'm assuming that my robot is pointed in this direction. Pardon my drafting skills, but it's not going to get any better, at this age. So here's the line. And you know what the heading angle is? It's easy to get confused. The heading angle is the angle made with respect to the x-axis, not that axis, this axis. So if you project this backwards, this angle is the heading angle. Is that clear? This is the current heading angle. Now, we want it to point in this direction. So if you extend this line, then the heading angle, you can take it like this, but that will be greater than 180 degrees. You really want to go this way. Is that clear? This line projected this way will hit the red axis somewhere here. So the heading angle is the angle with respect to the red axis. So all the way here. All the way here. Is that okay? It's going to be greater than 180 degrees. But we're going to calculate it. I've used some sample values here, which are too small to read, but I'll
6 and 8.
6 and 8. Yeah, help me out here. What is this?
4 and 6.
4 and 6, right? So you should be able to calculate it from there. Simple trigonometry. But you have to be mindful of, is it greater than 180 degrees and all of that. That's what this program is cleaning up. So let's go further. The calculations use degrees for our convenience. However, it needs to be done in radians. So you can do a final conversion. After you do all the error and all that in degrees, you need to convert it to radians. You know, that we can do later. In your code, MATLAB has a whole bunch of inverse tangents. Arctangent, A tan 2D is what you want to use, not A tan 2. A tan 2 is in radians. A tan 2D is in degrees. Now perhaps radians is more easy, but then you don't require a final conversion, right? But I'm telling you that degrees is easier for us to perceive. So therefore you want A tan 2D. Not only that, this is the robotics angle result. 0 to 180, 0 to minus 180. In other words, minus 180 to plus 180, not 0 to 360. MATLAB has a tangent that also does 0 to 360. Don't make that mistake, because it won't fit in with robotics. So we are going to convert to radians. But any angle which is greater than 180, okay, let me give you an example. You get a result of 240. What is the robotic angle equivalent of that? 60 or 120? Because, what did I say?
240.
I said 180? No, I meant to say if you get an angle of 240, I thought.
180 minus 240 minus 60.
No. So you're going 240 this way, right?
Minus
You have to go this way. So minus 120. Right? So this wrap function will convert into that. So there are many wrap functions again. Wrap to 180 degrees, right? Wrap to pi. But wrap to 180 will give you the result in degrees. Wrap to pi is, it's better to convert to radians finally, right? So I think we're going to go with wrap to 180. Now look at the code. XR is equal to 6, YR is equal to 8, correct? See, all the answers are here. Run it again. Waypoint 4, 6. I deliberately made up these numbers because it teaches you a lot. Here's theta d, heading angle. Desired is A tan 2D. This is how you're supposed to treat it. YW minus YR, XW minus XR. Not the other way around. How did I find that out? I went and looked at the MATLAB help file. So there's no need to guess, because MATLAB documentation will tell you that the Y increment comes first, X increment. Do you get it?
Yeah.
This is the Y increment. See, green axis, Y increment, X increment. Try a few examples. If it doesn't work, then you know you're doing something wrong, right? Theta desired is this, using MATLAB's A tan 2D. It turns out to be minus 135. Theta current, or actual or current, C for current. Current is this angle. Now that you can't find out from any, you have to assume that, look at it, 135 is a good value for that, right? I don't like the fact that both are 135s, because then you'll get confused. Are you supposed to get the same number there? No. It's just my example, bad example, because I shouldn't have chosen 135. It will confuse people. That is not my intent. So it's 135. No reason it's the same as that with a negative sign. So error, problem, right? Minus 270 is the problem. You got to wrap it. So I wrapped it, and the answer is 90. Do you agree? Minus 270 is 90. So if you're writing a program, you have to take all the elements that you need from here into that program, right? So I've given you an example. You can borrow whatever you want, and then see A tan 2D, 4-quadrant inverse tangent in degrees. Wrap to 180, wrap angles in degrees. I wrote these down as comments to myself, because if you want to, after 6 months, you come and say, how did I do that? Just look it up here. You got code. Okay, the other program was Euler or something. So converting from Euler to Quaternion and back. Now right now we are assuming we don't know what quaternions are. I'm just telling you how to convert it because you'll have to take a part of this program and take it into your main program. Just like the other one, the heading calculation. A piece of this program will go into your own program. Right? Remember the exercise I'm going to give you? So specifications and Euler angles need to be converted to quaternions. The robotics, you have to work with quaternions. Euler angles are convenient for us. Assume that the robot needs to be rotated plus 90 degrees. So we are using this to, remember, do the set model state. There the default of 0 degrees was fine. But here we're going to do it, what? 90 degrees. We are not 0 degrees but 90 degrees. Assume that the robot needs to be rotated plus 90 degrees around the z-axis and 0 degrees around the y-axis. See, you can't have any rotation around y-axis and x-axis, right? Because if you rotate around this, the robot is going to, topple over. This is the only legitimate rotation if your robot is on a plane. Is that clear? So you can't rotate like this, and you certainly cannot rotate like this. So that's why the other two have to be 0, 0. When applied to turtle-bot 3 positioning, the robot should end up by facing in the direction of the world y-axis. Do you agree? If I rotate like this 90 degrees, red axis, I should be pointing down the green axis. Now, the default axis convention, this is why, the real world of engineering is so complicated because you have so many conventions, and that's why engineers are paid good money. The default axis convention is this order, ZYX. That means the way you specify it, if you use the default notation, it is expecting rotation around Z first, then Y, and then X. If you put Z in the last position because you think XYZ is logical, no, it's ZYX. Got it? So you have to put the pi over 2 in the first position. It has to be in radians. Not 90 degrees, but radians. So pi over 2 0, 0. And then I do a very simple MATLAB function, Euler to quat, EUL to quat, and whatever number of degrees you want to convert. And here is the quaternion. Now you don't know what that means. I'm going to teach you this afternoon. Why that quaternion makes sense and why people need it. The quaternion is in this format. W, XYZ. XYZ has nothing to do with the other XYZ. So W is the first number, this one here. X is the second number. Y is the third number. And Z is the last number. It's hiding here somewhere. Similarly, the reverse conversion is possible using quat to Euler. Now, ready for the last part? I want to use this piece of knowledge. Now, if you can see it, okay? I think I know what it is. So you're setting up a desired position of 4, 2, right? And 0. So this time you're doing a 4 to 0 because I want to convince you the robot can be thrown anywhere. You can even toss it up into the air. You can play with it later if you want. You're not going to break anything because it's not a real robot. So 4 to 0. And then you also have to enter the model name and the reference name. So that's what is entered here. If you see reference frame, it is world. You see that? That means the rotation is with respect to the world frame. The model is a turtlebot 3 underscore burger because you can also move obstacles, anything there. You can move a second turtlebot 3 burger. So you have to tell it which one are you talking about that you want rotated or moved. And or moved. So you need the reference frame, word, model name, turtlebot 3 underscore burger, and then you need to add the position, and you can also add the angle for the quaternion. So I think not in MATLAB, but it's there in the program. It's there in the OLCL program. If you add to that, the angle, and you will change 0, 0 to 4, 2, you can send it anywhere you want. Now, this window you see here is how you do it in Ubuntu. This is with an Ubuntu set model state command. It's better to do it in MATLAB, because remember the original reason we did it. The turtlebot is jittering, right?
Yeah.
If you go and fix the jitter, and by the time you come back to the program, MATLAB program is jittering again, Not much use, right? So better to set the model state from within MATLAB. That's why the code is basically there in OLCL1. Let's look at it again. Reset turtleboard 3 to desired position here. So if you want to move it to 4-2, you can say 4-2. And then the quaternion, you have to figure out, this afternoon you'll be able to figure out how to define the quaternion to get the angle you want. We'll do that this afternoon. Remind you. We can move on to coordinate transformations. Next topic.
Yeah.
So keep these programs with you, because I'm basically going to say the robot is at 0, 0, 0 with orientation 0. And then I'm going to say go to this. We call it a waypoint. A waypoint is an intermediate goal. So go to waypoint 1, waypoint 2, waypoint 3, maybe waypoint 4, waypoint 5. You can have any number. And you're going to use heading control. You can't just drive straight for so much. And you're not allowed to turn and point, because that's not an efficient way to drive. So you're going to smoothly go through a bunch of waypoints and you'll be able to do it. Remember, we need to set up what? An outer loop that checks whether you're within the circle drawn around the first waypoint. Right? If that circle is too tight, you're making the job difficult. But maybe in demining, the robot is going to go find a mine there, take it out. Go to the second position, take out a mine. Maybe accuracy is important, right? So then you'll probably tighten it, but of course you want the robot to stop short of the mine. You'll have to figure out a way of the robot can't go over the mine, right? Because then it'll blow itself out. You want to defuse the mine, not blow it up. So you need heading control, because just checking whether it's within that circle is not going to work unless you're going in the direction of the circle. So you've got to constantly correct the heading. How are you going to do that? You're going to calculate the heading angle error. And then you're going to take the heading angle error, multiply by a constant. And omega is going to be Kp, omega, the turn rate is going to be Kp times the heading angle error. Choose a small value of Kp first. If you put too large a value, it will become unstable. Because, it's like doing this. So choose a small value of Kp. Outer loop is for as many waypoints as there are. Inner loop is while you're not pointing to the next waypoint, adjust your heading to point to it, and it's going to work. So this is like a good test for your skills. So one aspect of robotics is trying to drive to a goal, right? The other aspect is what? Avoiding obstacles. We'll do that next week. We'll avoid an obstacle. So you have the complete package at that point. Yeah.
So can you give any example value of Kp? How small it should be, 0.2, 0.5?
So I have a working program. Instead of trusting memory, I will give it to you this afternoon. Ask me again, I will pull it up.
Okay.
Yeah. I think it is I don't want to trust, but I'll give you an initial guess. I think I remember it was 0.01 or something.
Okay.
Something like that, but I'll confirm it this afternoon.
So it is in the 0.0 range.
Yeah, right.
Okay.
Yeah. 1 is too high. Yeah.
Yeah.
So my robot was kind of, turning around like this. Because it was such an overreaction, it was steering like that. If you have a PDF version, this is probably you've never heard of this word. It's a keynote presentation, which is Mac's equivalent of PowerPoint. And I asked you the question, well, first of all, y points to the right, everybody agrees. Z points up, everyone agrees. The answer is, it depends. Not that it points out. We are actually being pushed in that direction, but it could actually equally well point in, as she's going to show you. The point she's making is, we have to work with the right-handed convention. So if you want the right-handed robotics, the convention followed in robotics, right-handed convention, then if you turn X into Y, right? A screwdriver should advance in the direction of Z. So from that point of view, X should point out and not in. But the point she's making is, this could be a figure that could also represent axes where X is pointing in. Watch this. So let's get familiar with these two cubical boxes. So here we are seeing the bottom of the box. Can you adjust your eyes and confirm that? This is the bottom of the box. Here we are looking down to the top of the floor. So this is the top of the floor, this is the bottom of the floor. Is that clear?
Yeah.
Now why is she doing this? Because she takes the same axes and puts them in the boxes. So is X pointing out or in here? It's going in, right? You're looking at the bottom of the box. So X is pointing away from you. And here X is pointing towards you. So she says the same figure, you can interpret it either way really, But maybe you're so used to saying, okay, it's pointing out, but by forcing it into the box, she shows you that one of them is right-handed convention and the other is not. And we need to go with right-handed convention. But looking at the figure, you can't tell. You can, X can be either way. So we'll always use right-handed convention. Therefore, it points out. That's what she's saying. So you know the rule? X times Y, right? This should be Z. So the finger should curl from X to Y. My right-handed screwdriver rule is also good, but this also works. This is the direction of the finger. You have an idea why we need multiple coordinate systems in robotics, but now finally you'll get it with an actual example. So here is the plane, and here is the control tower, right? So the tower coordinates, right, or the tower axis system is what she means. X, Y, and Z. And you'll agree it's the right-handed coordinate system. It is the right-handed coordinate system. For whatever reason, planes apparently have Z pointing out of the nose. This is also a right-handed coordinate system. You can verify. If I turn X into Y, the screwdriver advances in the direction of the ZP. Do you see that? It is a right-handed system. So you're allowed to have another right-handed system. Nobody can force the plane to have X coming out of its nose. Just like a robot, right? Remember a robot? A robot's axis has X going this way. The plane doesn't. Apparently planes use this system a lot. So, can you see that something seen by the plane will have to be transformed for it to be seen by the tower axis system? So you need conversions like this all the time. Here it is a simple problem because it's only a 90-degree shift. You can have a shift of 33.85 degrees in general when a robot is moving. With respect to the word frame, the angle can be anything, right? So you need a process of transformation. You need a process of transformation. And it has to be automated. So that's what this topic is about. Here, we can solve all these problems formally, but here we can also look at it and solve it. Purely because there's only a 90-degree shift between these axes. You see? If I, so the Z is this way. If I go this way, if I take this coordinate system and go like this, then the Z and the Z will be aligned. So do you realize that there's a rotation shift, but there's also a translation shift? I first have to rotate the Z to point upwards, then this X will lie down flat. Right? And then you have alignment, but you have a displacement. You can't tackle the displacement until you first align. You have to first rotate it into alignment, only then you can look at the displacement. So first you have to rotate this and lay the y-axis flat. Z will be now pointing up just like this, but then you can deal with the displacement. And he's given some numbers here. 50-meter shift this way, 5-meter shift this way. And right now the plane is on the ground, so there is no shift in the vertical direction. Let me repeat. 50-meter shift this way, 5 meters from here to here. And then no shift. So, can you solve this mentally or maybe with pencil and paper? What is the location of the nose of the plane? The nose of the plane in tower coordinates. So along X it's 50. Along Y it is 5, and along Z it's 0. What is the location of the origin of the tower in plane coordinates? So this would be how much?
50 and
50, but in the last position, right?
yeah.
And then up, nothing. up is xp, so first position, right? And it's -5 because it's coming this way.
Yeah.
So it is opposite to the positive y direction. Location of the nose of the plane and plane coordinates, you know this already from the robotics example, right? It has to be, the nose of the plane always has to be 0, 0, 0 because it's carrying the axis. Now imagine if the angles are less than 9 degrees, right? It's a very complicated problem. A human being can set and solve 2 of these problems maybe in 15 minutes. Now you're going to grunt and with trigonometry and calculators and so on. You have to automate this. That's what TF does. So TF is transformation. The ROS, package TF deals with that. And I believe it's called TF2 in ROS 2 now. So now the plane is up in the air. So the plane is in the air, and you have now a new distances 30, 15, and 10. Can't read that, but whatever that is, 10. 30, 15, and 10 here in the notes area. He has it. So location. So you can finish this. Location of the nose of the plane. Nose of the plane in tower coordinates. Location of the origin of the tower and plane. Same questions. Location of the nose of the plane, plane coordinates. And you know that 0, 0, 0 is a answer for this. Is that okay? So now the plane is in the air, but still the axes are only 90 degrees apart. The problem will really arise for a human being when the angles are different from 90. Okay, now comes how to deal with translation. There's the reason they use this word. That's not super important, but we'll get to it once we discuss the method. So there is a trick that is necessary for this homogeneous. So you know what homogeneous means? I was going to postpone it to later, but maybe not. So homogeneous means you have one matrix that takes care of both translation and rotation. So before quaternions, this was the method everybody was using. One matrix to do both translation and rotation. Except there is a problem of gimbal lock. That's why quaternions were introduced. We'll get to that this afternoon. Gimbal lock, right? But homogeneous takes care of both. And the people who most use transformations is, you'll never guess, it's the programmers in the gaming industry. So the gaming is a very huge, right? In Japan, in the US, maybe even here. There are people who write software for games, video games. So a lot of transformations are involved there. Because there are things that are moving, and maybe your hero needs to know where the villain is, right? So you need the coordinates so that you can design a path to get to that place, or climb a wall or something. You need to know where the wall is. So you need transformations a lot in the gaming industry. All the older gamers, they use the homogeneous transformation using matrices, 4x4. You'll see it's a 4x4 matrix, but the problem is gimbal lock. Quaternion came later, it solved the problem of gimbal lock. So the gaming industry is kind of split now. The younger guys use quaternions because they're able to understand the math. The older guys don't use it, they try to work around it somehow. And this afternoon we'll find out, what quaternions are and what you need to do if you want to avoid quaternions and still solve the problems of gimbal lock. And there's also another thing called interpolation. You can't get smooth interpolation with homogeneous transformations. With quaternions, if you make a motion like this, the interpolate, right? So there are many different points here, right? If you have somebody wielding a sword in a video game, then basically this path is calculated based on interpolating that and this, right? This is the start position, this is the end position. So quaternions are used to interpolate the angle. If you do it with regular angles, Euler angles, it's not smooth because the angles don't linearly map, but quaternions they do. So how do you get around that with the older gamers? Just sheer programming ability. They figured out how to space it out evenly, even though the angles cannot be spaced evenly. So they figured it out, and they refuse to budge because people are set in their ways, right? Particularly when you've been doing programming for games for 30 years, it's not easy to change. And that's a problem all of us face at some point in our lives. We don't want to change. So, in order to accommodate the homogeneous transformation, that's what I say here, you have to add a 1. You can also add a 2, 2, 2 and 257, but this is not a math class, so we're going to just stick with 1 and a 1, 1, 1 there. So the fourth row, you call it a waiting for, I don't care what you call it, we just want to know how to do it. So you lengthen it by 1 by adding a number 1. So here's the problem that finally, if you didn't get it so far, should convince you that we need transformations. Here is a camera that is on the wall. It's a fixed camera, but it could also be moved. Therefore, it needs its own axis system, correct? It has to be a right-handed coordinate system. Here is a widget or a part, another name for a part. Here is a robotic arm with a gripper, and you need to go and pick up the part. So the camera, apparently there is no camera here. So the camera on the wall is going to say, hey, the widget is here. But of course, the widget has to be told, the gripper has to be told where the widget is in its own frame, right? What does it care what the camera sees? So you have to do a frame transformation. So here is the world axis. So you have to do a transformation from there to the world. And then there's another rotating joint here in between. So basically you have to go from here to here and then go here. Is it clear? You can't go directly from here to here because the orientation of this is also determined by the orientation of this. That's how complicated the world of robotics is. This is the fixed robotics, the articulators. But imagine if you have 5 robots running around, each one of them has got 2 cameras and a LiDAR. Let's say there are multiple cameras on the wall. Let's say that these are pivoting cameras. And now you get a really big problem, a mess. So you can't develop good maps until you synchronize what every robot is saying from its own neck, right? The camera is like a neck. So, and the neck can rotate, right? You can have a rotating camera just like we turn around like this when you're driving. So you have to coordinate all that in order to create a good map. Otherwise you'll be placing stuff all over the place and the map will be totally useless. Okay, so let's get started. We're going to define the transformation, but we go slowly. So we are dealing with translation only. The first part is translation only. And just a reminder that all these are equivalent words for the same thing. Inertial, reference frame, global frame, world coordinates. It's all the same thing. We'll use world, okay? Sometimes you might say inertial, but it'll be clear. So world, see, XW, YW, ZW. XR, YR, ZR, robot. Is that okay? And right now, there's only one translation in this direction. No rotation. You can see Y, Y, X, X, Z, Z. They're all aligned. So we start slowly, 3 units. So we have to move the robot coordinate system minus 3 units to align with the world. Do you agree? So there's 2 ways of looking at it. Move the robot coordinate system minus 3 to align with the world, or move the world system plus 3 to align with the robot. Right? They are equivalent. You'll find that the method requires you to look at only one of them. Methods are what? Being organized. So you can't use one or the other because the way the method is framed, you have to use one of them for transforming from one frame to the other, and the opposite for transforming from the other frame to this one. So that's the method. The process is laid out that way. Now, you know that if I give you a problem like this and I say, okay, there's a point here, the robot frame that is 5, 6, 7, you can tell me the answer, right? Just by looking at it, you'll be able to read off the answer. The only adjustment needed is in this direction, right? So the advantage of this is, if you're studying for a test, and you're trying to figure out whether you know the method, then you can form your own problems like this. And therefore you can try using the matrix to transform it and see whether you get the same result. Because the answer is very clear to see in this case. So translation along one axis, that's the same problem. Convert from world coordinates to robot coordinates. So world, all these are world, 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 world. 0, 0, 0, 1. The 1 is just, the weighting factor. So 0, 0, 0, the origin. What is it on this axis? So it will be definitely 0 and the last one will be a 0, right? Only the y is different. Convert from world coordinates to robot coordinates. So suppose you have a point. Should you subtract 3 convert from world to robot coordinates. So because you have 3 in this direction, right? Any y coordinate, you have to subtract 3 to get the y coordinate on the robot frame. Does that make sense? So he's got the answers here. You can see the notes here. So do you agree 0 minus 3, 0 is the answer? Do you agree? This is the answer. 0 minus 3, 0. The 1 is just the weighting factor. Don't agree? You agree? So the transpose is because typically you write vectors as a column vector.
Yeah.
And to save space, we write them this way. So we had to put a transpose. Now, what about the second question? 0, 3, 0, 1. Oh, that's perfect. The 3 cancels. So if you have 0, 3, 0 on the world axis, it will be 0, 0, 0, right? It will be exactly this point. So this answer is correct. Third one, 5, 10, 15. So you know all the activity is going on at this level. So subtract 3 from here. 5, 7, 15, 1. Got it?
Yeah.
And then finally A, B, C. See, this generalizes it now. A general problem A, B, C will be A, B minus 3, C and 1. So this handles a single translation. But we have 3 translations in general.